Another case where exponential decay is rather useful is in the science of carbon dating. So carbon dating takes what's called the half-life of a substance. The half-life is the time required for half of a substance to completely disintegrate. We know the half-life of carbon-14 is approximately 5,715 years. This means that after 5,715 years, half of the carbon-14 in the sample will no longer be present. So first off, we're going to create the half-life of carbon-14, and we're going to use that to create the exponential decay model. Okay, so for part A, how I'm going to approach this is to know that after t equals 5,715 years, half of the original amount will be there. So half of A naught will be there. The way to say that is A, the amount, is 1/2 of A naught. Okay, that's a way of saying the half of the original amount. So what I'm going to do is take my exponential growth function / model, A equals A naught e to the kt, and start plugging in some different things. For A, I'm going to change that over to 1/2 A naught equals A naught e to the 5,715 times k. So I'm putting that number in for t up above there. Now what I can do is I can actually get rid of the A naught from both sides. Since there's an A naught on both sides, I can divide that out, and it will go away, leaving me with 1/2 equals e to the 5,715 k. Now what I'll do is I'll take the natural log of both sides. So we have here ln of 1/2 equals, keep in mind again, ln is log base e, so log base e is going to cancel out with the e, and we'll be left with 5,715k equals ln of 1/2. So I can divide out this 5,715 from both sides, and that's going to leave me with k. K is ln 1/2 divided by 5,715. And that's going to give us a pretty small number, so let's round it off. I got approximately negative 0.00012. So since it takes so long to decay, the decay rate is a very small number. But what that tells us is the actual decay rate of carbon-14. And so the actual model function for this carbon-14 goes A equals A naught e to the negative 0.00012 t. Now the next part of this question says the Dead Sea Scrolls were found to contain 70% of their original carbon-14. With this information, let's approximate their age. Okay, so how we interpret this information, 76% of the original carbon-14. That means that the amount they contained, which is A, is going to equal to 0.76, 76%, of the original amount A naught. So that's what I'm going to be able to use to substitute in for A. I'm going to take my model from the last example. For A, I'm going to put 0.76 A naught, and then that's equal to A naught e to the negative 0.00012 t. And now I'm going to divide out the A naught from both sides, because that way I can get rid of it. from the equation. 0.76 equals e to the negative 0.00012t. Now, like we've been doing so far, when we have e and we're trying to solve, we'll take the natural log of both sides. ln 0.76, we of course recognize that ln and e is going to cancel because of the log base e is the same thing as ln. So we're going to get negative 0.00012t is equal to ln of 0.76. Now we can divide out both sides by that long decimal number so that we can solve for t. Okie doke, and once we get that out of the way and do the calculation, again, we'll need to leverage the calculator to give us a number for it. I came out with approximately 2,287 years. Now that's how old they were in 1947. So in the year 2020, we're dealing with 2,287 years plus an additional 73 years. So that's 2,360 years old in the present day 2020. Okay, now this question here tells us that the element krypton 85 has a decay rate of 6.3% per year, or in other words, negative 0.063. With that information, we want to find the half-life for krypton 85. So we'll take that information. The decay rate is negative 0.063. And we're going to answer the question, how long? In other words, t has to equal to something for the original amount, a, to equal to 1/2 of the original amount, a naught. That's going to be the question we try to answer here. So we're going to use our exponential growth or decay function, a equals a naught e to the kt power. We're going to substitute in for a 1/2 a naught to stand for the half-life that we're dealing with. We also know that the value of k for the decay rate is negative 0.063. So I'll go ahead and put that there. Now what I can do is divide out the a naught from everything. That'll allow me to get rid of it. So we're going to have 1/2 equals e to the negative 0.063t. We can then take the natural log, both sides. So we're going to have ln of 1/2 equals log base e of e raised to the negative 0.063t, for which we can cross out the ln and e, log base e and e. So negative 0.063t is equal to ln 1/2. And we can divide out the decimal to both sides. And so now we can figure out what t is equal to. If we put that in the calculator, it comes out to be approximately 11, rounded to the nearest whole number, 11, in this case dealing with half-life, years. So it takes 11 years for the half of the substance to disintegrate.